So the aortic pressures are really important as it pertains to blood pressure. And this is basically measuring the pressure that's happening throughout these phases in the aorta itself. So we start up in diastole, and diastole is, again, phase 1 and phase 4 here. So all of this is representing diastole. And we start up with the aortic valves closed, right? And so blood is still leaving the aorta, and so the pressure begins to fall here. So we can see this drop in this curve, indicating the drop in pressure throughout the artery as the aortic valve closes. And so the lowest point, the lowest number that we get to, which is this reading here, is called our diastolic pressure. So I'll say that in a different way. Our diastolic pressure is the lowest pressure that we measure in the artery as the pressure drops after the closure of the aortic valve. Okay. Systole is when the aortic valve opens. Now, remember, systole is that ejection phase, so the aortic valve is now open. Pressure is rapidly rising, right, initially, and then dropping as that blood actually leaves. And so we can see that here, right? This curve is representing that systolic phase. And so the highest point that we can read during that systolic emptying phase is called the systolic pressure. And so that is going to tell us about the highest recorded pressures in our artery during at the middle of systole. Now, towards the end of phase 3, towards the end of systole, we typically see this backflow of blood. So as that valve closes at the end of phase 3, as the semilunar valves close, as the aortic valve specifically closes, we see a bit of blood kind of rush back towards the closing of that valve. And so there's a kind of a dip and then a sharp rise in the pressure as a result of that slight backlog or backflow of blood against the closing valve. And that gives us what's called the dichrotic notch in that curve. So we measure the systolic pressure, the highest point in the middle of phase 3, the middle of systole, and we measure the diastolic pressure, the lowest point at the middle or at the middle of phase 1 or the middle of diastole. Okay. Now we can take the systolic pressure, we can divide that by the diastolic pressure, and that gives us the MAP, or the mean arterial pressure. And so the mean arterial pressure is really an average of the pressure in the aorta that's occurring during an entire cardiac cycle. And this is a very helpful value. It's going to tell us about the average driving force of blood that's pushing this blood throughout the systemic circulation. So basically, I can take my highest reading in the aortic valve, and I can take my lowest reading in the aortic valve, and I can average those two values, and that's going to tell me about the average pressure with which blood is moving throughout the entire systemic circulation. So it's a very meaningful, very important clinical number that we look at to determine the overall efficiency of the heart at vascularizing the entire systemic circulation. So the continuous blood flow through the cardiac cycle is maintained by the state of the elastic aortic artery. And I'll talk about how this blood flow is maintained continuously on the next slide. But essentially, the aortic valve can act as a pressure reservoir because of the elastic nature of this artery, meaning that this artery kind of collapses on itself. Think about a really stretchy or brand new rubber band that's really elastic. It's going to be able to capture some of the pressure when it's extended, when it's filling, and it can take that pressure and recoil that pressure during the filling phase in order to keep the blood continuously flowing during all points of the cardiac cycle. So the elastic nature of the aorta can store energy during systole as the walls expand, and take that energy and release it during diastole as the ventricles fill, that valve is closed, and it can keep the blood forcing, it can keep the artery forcing the blood throughout the systemic circuit, even though that valve is now closed. And so this entire phenomenon is what allows us to keep the aortic pressure continuous and keep it flowing evenly throughout all parts of the cardiac cycle. So let's kind of explain that a little bit better here. So basically during systole, the aortic valve is open, blood is flowing from the left ventricle. Remember, the left ventricle is the preceding chamber that makes that blood move into the artery. And so blood is leaving the left ventricle, flowing through these aortic valves and making its way into the aorta here. And so during systole, as that blood is moving, we expand this elastic aorta and we kind of capture that pressure and we kind of store that pressure in the walls of this elastic artery. And we're going to use that during the next phase. Okay. And so that blood is going to make its way out to the systemic organs, but we're going to also be storing that pressure for when the valve is closed. So during diastole now, the valves are closed. And one would think because the valve is closed, we have an interruption in the pressure that is allowing blood to flow out evenly to the systemic organs. One would kind of think that. But the reason that that is not true is because of that energy that we've now stored in the elastic artery. We can use that energy now as this elastic recoil that kind of forces or propels the blood along during times when the aortic valve is closed. And so as I mentioned earlier, it keeps the flow to our systemic organs continuous and steady, even when the valves are closed and during all parts of the cardiac cycle. It keeps the vascularization of the systemic organs continuous, even at times when the aortic valves are closed, that elastic recoil of the aorta. Okay. All right, let's now talk a little bit about the ventricular volumes. And so this is basically the amount of blood that is sitting in our ventricles at different parts of the cardiac cycle. So the first volume is called the end diastolic volume. This is the amount of blood in the ventricle at the end of diastole. Remember, diastole is the filling of the ventricle. And so this is going to be a pretty big number. After the ventricle has completely filled, and we go in and we measure how much blood is sitting in that chamber. And if we think about when we would actually calculate the end diastolic volume, it would have to be at the end of diastole. And we know that diastole ends at phase 1. So at the end of phase 1 or any time throughout phase 2, because really phase 2 has this isovolumetric phase, so the volume is not changing here. So we can measure the end diastolic volume at the end of phase 1 or any time throughout phase 2. The end systolic volume, on the other hand, is the volume that's sitting in that ventricle at the end of systole. So after I've just ejected blood from my ventricle, that blood is now moving into the artery. What's left? What's left sitting behind at the end of systole? I can go in and I can measure, and I'm going to get my end systolic volume. And once again, we would measure the end systolic volume at the end of systole. Remember, systole is phase 2 and phase 3. So at the end of phase 3 or any time throughout phase 4, we would be able to measure the end systolic volume. Remember, the volume does not change in phase 4. This is one of the isovolumetric phases as well. And then we can get stroke volume. So we can take the amount of blood that's sitting in the chamber after it completely filled, and then we can go in and measure the amount of blood that's left back in the chamber after the chamber has emptied, because the chamber, the ventricles never completely empty. And so we can take that filling volume and minus the amount that's left after it has emptied, and now we can get our stroke volume. So it's going to tell us the amount of blood that was actually ejected from that ventricle. So stroke volume is a measure that we can calculate based upon the total end diastolic volume, all that the chamber has filled, minus the total end systolic volume, what's left back in that chamber after we've ejected blood. And so the typical values for these measurements are about 60 mLs for end systolic volume, 130 mLs for end diastolic volume. And so we usually can calculate about 70 milliliters for our total systolic volume. And another way to say this is that the heart completely fills about 130 milliliters at the end of diastole. It's going to squeeze out or eject about 70 milliliters throughout systole. And then if we were to measure what's left at the end of systole, our end systolic volume, we would only see about 60 milliliters left sitting in that chamber. So the heart always keeps about 60 milliliters of blood in it at all times at the minimum. Okay. And then from those values, we can now think about the ejection fraction. So the ejection fraction is a fraction of the end diastolic volume ejected during a single heartbeat. So if we took our stroke volume, which is how much blood actually left that chamber, how much was ejected, and we divide that by the total amount of blood that we filled in that chamber to begin with, it will give us a percentage of how much does the chamber actually empty, right? 70, which is our stroke volume typically, divided by 130, which is our end diastolic volume typically, gives us a fraction of about 0.54, which is about 54%. And what this tells us, what this ejection fraction tells us, is how much is the heart emptying, right? How much is the heart really emptying at rest? And what we see is that at rest, the heart empties about 54%, and the remaining is left inside of that chamber, that's 60 milliliters of blood. And so if we look at those volumes here, once again, we can correlate that to what's happening in other parts of the cycle. So we start out with the chamber gradually filling here. So this is phase one. We gradually fill blood from the atria down into the ventricle. And then throughout systole, we're ejecting that blood. So we go from this 130 milliliters, which were filled in that chamber, which is our end diastolic volume. During phase three, when we begin ejecting that blood, take note here that during phase two, the volume is the same. So there's a slant representation of this curve, which shows that the volume is not changing at all in phase two. At the start of phase three, we eject that blood until the volume drops off rapidly. Okay, it goes all the way down to about 60 milliliters. Another thing to note here, it does not completely empty. So there's always 60 milliliters at the minimum sitting in our ventricles. We then get into phase four, which again, we see that the volume is not changing here. This is an isovolumetric phase as well. And then from there, again, we see the filling of that chamber once more, which is the start of diastole, the start of phase one. Okay. And so we go from 130 milliliters, we eject 70 milliliters, which leaves us with 60 milliliters sitting in that chamber, and then we fill back to 130 once again. Okay. All right, and then we'll look at the pressure volume curve here. So if we took that information, the information about the filling of the chambers, right, the volume, and the information about the pressure changes with this, which is the Y part of this curve, we can then come up with the pressure volume curve, or the pressure volume loop, this is sometimes called. And so we can see here that phase one is our the initial part of our cycle. So we start off here filling blood from the atria to the ventricle. And so we see the volume rise, the pressure rise slightly, but more towards the end of this phase. So the volume is what's rising here in phase one. And then we get into phase two. Notice phase two has no volumetric change. The volume remains the same. So the pressure steeply rises and there's no change in the volume, phase two. Then we get into phase three. Here's where we're ejecting blood from this ventricle into the artery. And so we see that the volume decreases. So we see this backward loop of the curve, which indicates that the volume is now decreasing and the pressure is slightly rising, but then it's going to eventually drop off towards the end of phase three. This is that attempt of the ventricle to squeeze the blood out initially, but as that blood moves out of the chamber, the pressure then falls. And then we get into phase four, again, another isovolumetric phase. The volume is not changing here. The pressure is gradually falling until we get back to phase one. So remember, phase two and phase four are our isovolumetric phases. The volume does not change in these phases. Instead, the pressure is rising in isovolumetric contraction and the pressure is falling in isovolumetric relaxation. Now we can take information about this curve and tell us a lot about how the heart is filling and emptying adequately. If there's too much blood in the heart, let's say we have a cardiomegaly, let's say we have a backlog of blood in the heart, this curve is going to be shifted to the right? The volumes are going to be higher. And so the curve is going to shift to the right or become wider. And so we can use this curve to tell us about the way that the heart is filling, the way that it's emptying, how the pressures and volumes are changing appropriately. And so we can see a lot of abnormalities to this curve that will give us indication about the health of the heart and how the cardiac cycle is working appropriately or not. But this is a normal pressure volume curve, which has these normal filling and emptying and rise and drops of the pressures for these phases. Okay. And then the final bit here that we're going to talk about is the heart sound. And now I want to point out early, and I want you to make a note of this in your notes. The heart sounds are not due to the opening of the valves. They're not due to the closure of the valves. The heart sounds are due to the turbulence of flow against a closing valve, a very specific phenomenon here. It's due to the turbulence of blood against a valve that's trying to close, okay? And so the first heart sound is a soft lub, that is the closure of the AV valves, both of them closing simultaneously. This is that increase in pressure backflowing towards the atria as the AV valve closes, right? So against the back of that closing valve, the turbulence of the blood trying to squeeze past. Then the second heart sound is a louder dup that's created by the closure of the semilunar valves and the blood that's hitting from the ventricle, moving into the arteries and hitting the back of that closing semilunar valve, okay? And so we have this very soft lub and a higher pitched dup. So there's this lub dup, lub dup, lub dup. And there's that difference in the pitch because of the difference in the amounts of blood that are hitting against those respective valves. So the softer lub, the first heart sound, is the closure of the AV valves and the blood moving against the back of the closure of that AV valve. And then the second heart sound, a higher pitched sound, is the sound of the blood moving against the back of the semilunar valves. Okay. And we can see that represented here with the lub being the closure of the AV valves here, and the, the lub being the closure of the, here we go, the lub being the closure of the AV valve, so phase 4, we've got the AV valves closing, and then the dup being the higher pitch closure of the semilunar valves, which is phase 2.